Okay, guys, let us restart. Please come to the stage, or not to the stage, but to your chairs. Lars, der Audio ist eingestellt auf das HDMI. Der Audio. Nee, aber dein Rechner gibt über HDMI aus. Okay, gut.
Soll ich ausprobieren, oder?
Ja, probieren wir mal aus. Gut, lauter geht hier nicht. Okay, so with a little bit delay because we had to reconfigure the streams, we are back to the afternoon session, and I'm very happy that for the afternoon session we could win Falko Dressler, whom I know for quite a while, and I was very happy when the Einstein Center came to me and said, oh yeah, we have someone, he's called Falko Dressler. And now I even learned that he's the successor of Adam Mollisch, who is also a very famous professor, not only in Berlin and Germany, but all over Europe and the world. So, as I told you, we have the first class speakers present. And Falko will be talking about something that also has a very interesting title, which is Hybridized Cyber-Physical-Systems. Those of you who watched already the trailer know a little bit what it's about. As usual, we'll also watch the trailer in a second. But in the meantime, let me present to you Falko Dressler. So Falko is a full professor and the chair for telecommunication networks at the School of Electrical Engineering and Computer Sciences at TU Berlin. He received his Master of Science and PhD degrees from the Department of Computer Science of the University of Erlangen in 1998 and 2003, respectively. Dr. Dressler is an IEEE Fellow as well as an ACM Distinguished Member. He is a member of the German National Academy of Sciences and Engineering, ACATEC. His research objectives include adaptive wireless networking, sub-6 GHz, millimeter wave, visible light molecular communication, and wireless-based sensing with applications in ad hoc and sensor networks, the Internet of Things, and cyber-physical systems, of which we heard already this morning. Good, so as announced, let's watch the trailer and
I will talk about next generation of cyber-physical systems. So I have been working a lot on one particular application scenario for CPS, and that is automotive applications. So we have many autonomous cars these days, for example. So it's typical CPS. And we as engineers, we look at the problem with very engineering-focused mindset. Unfortunately, this excludes the user and the human in the picture. So our CPS is not alone. It's actually there interacting, exchanging information, and dealing with different, let's say, objectives with the user, with the human. Human bringing expertise, human bringing experience, the machine bringing quick reaction times, bringing amazing machine learning capabilities these days, and how the human user and the machine now form together a hybridized CPS, where autonomy can be exchanged more to the human side or more to the machine side. That is what we will talk about.
And that sounds very exciting, and therefore I hand over directly to Falko.
Thanks a lot for the invitation. Real pleasure being here. I missed the morning session. So sad. So I have not much of an idea. What is your background?
Irgendwie
what
war
you're
es
really
schön
working
zu
on?
hören. Also, dass wir immer klüger werden.
So I try to give you some entertaining session, but at the same time, I also want to have some interactive session. So whenever you have any questions, whenever there's some doubts, some concerns, some need for discussions, just stop me. Just any point in time, really, because I mean, I'm here for you, right? So you're not here necessarily for me. So I'm here to help you, to guide you, to discuss with you, and hopefully you gain a lot from the session. So. Hybridized cyber-physical-systems. That is a topic that kind of interests me since a long time, actually since maybe 10 years, 12 years, even though the name hybridized cyber-physical-systems is something that we only coined 3 years ago. But the human is an important component in our technical systems. And I guess most of you have a technical background. Is that? Some of you are nodding, that's fine. So as an engineer, we try to design technical systems. Are we doing it in the right way? Are we using the right metrics to investigate the performance of our systems? That's an interesting question. So that is something I kind of said, an additional teaser. So besides the video, I wanted to bring as a motivation, as a startup. I have 2 slides just to introduce me. Mark Oliver already did most of it. So I'm heading the telecommunication networks group here in Berlin. This is the current group. This is a very recent picture, actually, from our research retreat. Finally, we can do research retreats again, which is cool. So we can have summer schools in person again, which is even better. So it's something I really enjoy. So I'm a telecommunication networks person. So meaning I'm doing research on wireless communications, all the fields, right? Classical RF, millimeter wave, going to terahertz now, but also visible light communications, ultrasonic, everything that is communications. So that is what I'm interested in. But at the same time, we apply more and more methodologies from related fields into our research to make it eventually more efficient. And I'm very happy. And that's also something I want to invite you all the time doing. I'm very happy to have many collaborations. So we have an international research network. And that is something that you are just building up. And that is something that is the most important thing for any researcher, because you can rely on these connections, on this network, whenever, wherever you are. So when I'm traveling today to a conference, so I was meeting people, right? So it's family. So and you are now the junior folks in this family. So I mean, just join this research network. Talk to other people. Talk to me. Talk to others. Whenever there are questions, right? This is what we are about. So today I'd like to talk, of course, about hybridized cyber-physical-systems. So in the video, I very briefly mentioned that I did a lot of research in the last years with a very strong application focus on automotive. So we had many projects, many research activities in the field of using CPS ideas for automotive, how to have cars communicating, how to do cooperative driving, enable cooperative driving, and so on and so forth. So I have 2 slides that I always use in any talk when I try to set the scene, and that is the first one of them. Sorry, this is the first one of them. So there are 2 ingredients for this modern next generation cooperative driving. Number 1 ingredient is we have autonomous cars. So this is a very famous one, by the way. Anybody noticing what this car is about? You're too young. Say again? Exactly. There was a big challenge, Grand DARPA challenge at that time, having autonomous cars driving from the East Coast to the West Coast in the US, and that was the first car who managed it. So it was a long way going there, right? Today, these cars may look like this, or we may have platoons of cars driving on our roads today. Honestly, today, so there are licensed autonomous driving for trucks in Germany on 2 or 3 motorways now. So you can see them just by chance. So it's no longer a fancy idea, right? And the second ingredient, the second slide, second ingredient is communications. So because all these autonomous cars, and you have seen the many sensors on top of this car, very expensive by the way, you have LiDAR, you have radar, you have cameras, 360 degrees. So, but whatever you use these sensors, all these sensors have the same property as your own sensors, your eyes, your ears, they have line of sight property. So these sensors can sense anything they can see, visually see. Huh? So, but if there is something that they can't see, like in this situation, you are here in this blue car, you're seeing the green light, the car in front of you slowly speeds up, what are you doing? You go on, right? Otherwise people in the back, particularly in Berlin, will start honking. The same for the autonomous car. It will start moving. But what they don't see, neither you nor the car, the autonomous car, is that in this very moment something critical happened. Because it's not in line of sight. So the only way to get rid of this problem is communications. And there are tons of different communication protocols out there. Nothing to yet, or not necessarily, at least still to be invented. You have Wi-Fi, you have 5G now, 6G is at the horizon. You have a protocol that's called DSRC, that is Wi-Fi for cars, in short. There are many, many more protocols coming. There is visible light communications, there's millimeter wave communications, direct line of sight communications, and probably some of you will come up with this 2030 technology. So all this is there. So this is no longer fancy ideas. All these technologies are there, but still we are not living in this dream, right? We can see autonomous cars from time to time. So some of these cars have permissions to drive, even in Germany. So sometimes we can see by luck, by sheer luck, but you can't go out to the next dealer and buy one. There's many problems. No? Non-technical problems, a lot of them, liability issues and so on and so forth, but also technical problems. And I have one line here that I on purpose made as an animation. There are still fundamental research questions open, particularly about scalability, resilience of the systems. So German Research Foundation just started funding a new priority program on resilience in computer networks. So how can we make sure that it really works? Whatever happens, if there is an attacker, if there is somebody misusing or just falsely using communication technology, and cars don't work anymore. No? So there's many of these problems. Whenever you look around, what currently happens. Let's stick for a second with the research in Germany, but the same thing happens everywhere in Europe, everywhere outside Europe, internationally. So. Germany just started last year these big 6G initiatives, right? So there are these big hubs, research hubs all over Germany, new projects coming. And what is the research about? So it's a very interesting question. And one of the challenges that was there already with 5G is bringing latency down. But latency is only one of the ingredients. I always steal, every year I make a new copy, this slide from Gerhard Fettweis in Dresden. So probably you have seen this slide 100 times already. So he maintains the slide very nicely. So this is what is the trend in communications, telecommunication networks. One line, the blue line is Wi-Fi, the red line is cellular. You see at some point in time they will meet somehow. So we have data rates like crazy. Why do we need new research? Why do we need new research? Is it really necessary to do something more? Think about it. Think about it. So this is also something I'd like to, bring as a message today. Think about what are the real research challenges, the real opportunities. So what is really open? And possibly we don't need it, but possibly we need it. So this is still a bit undecided. And possibly we need it because we have so many more devices to communicate with each other than before. And I'm not talking about human beings. So I mean, yes, everybody of you, I'm very sure, everybody of you has 2, 3 devices, communication-enabled devices with you. So in this room we have 100. No.
watches, smartphones, computers. Very sure that many of you have more than 3. So, but this is not really the scale that we are interested in. The real scale comes from all these embedded systems somewhere in the lighting, in the smart city control and actuation of the entire environment we are living in. And then we are talking about billions of devices in a single city. And that makes a difference. That really makes a difference. And many of these applications running in these devices are very interestingly not just sensitive in order to get communications at all or getting high data rates, but they are particularly sensitive in terms of getting low latency, getting resilience, so making communications possible, whatever happens. If there is somebody jamming a Wi-Fi spectrum, communication must go on. Otherwise, it might be safety critical. Life might depend on it. There is just a buzzword I'd like to mention that you probably heard about. There's this Tactile Internet initiative that IEEE ComSoc initiated that 5 years ago, I think now, looking into particularly very reliable, very low latency communications that still moves on. So what do we do with that? I have a small video. I hope it works on the screen. This is a simulation. First of all, it's a simulation. It's not real life. Second, that is something we did already 10 years ago. So it's a very old simulation. The video is very old. I still like using it because it shows many of the challenges that are still unsolved after 10 years of research. What you see is a couple of cars. So some cars going east-west, some cars are going south-north, and they all approach this intersection and they go over this intersection and they pass this intersection without any collision. Positive side. Secondly, they pass this intersection without much speeding up, slowing down. So it's quite efficient. So both in terms of time and as well as let's assume it's electric cars, electric energy consumption. So it's very, very, very efficient. Let's assume we have that, we do a test drive this afternoon out there. Let's get 8 cars. Just put it there. Remove all the other cars. Who would volunteer sitting in one of these cars? Excellent, excellent. We have 1 volunteer. I would volunteer as well. And we are safe. I tell you why. So it's safe. It's really safe. And it's safe because I remove all the other cars, so there's no other obstacle. It's 100% technical system. Now we are getting slowly to this hybridized cyber-physical-systems, right? It's 100% technical system. Human is completely out of a loop. There's nothing that could go wrong. We have multiple communication links. So we have the yellow links, that is a 5G link. We have these red links, that is a Wi-Fi link. We remove all the other users from the same spectrum. And I'm pretty sure it's entirely safe. We can do that. Unfortunately, there's one artifact in my story that doesn't work in reality, so I cannot remove everything else, right? Just for the sake of this intersection approach. So that's why there's still a lot of research needed. So how can we make that possible, even so there are many other, let's say, users around? So let's talk a little bit about what really the human impact is. And I'm sticking with this automotive application example. So let's take the following example. Simple platoon, 3 cars, all the 3 cars driving fully autonomously. Safety gaps are maintained by a CPS, so there's a control system running, there's communication running between the cars, everything is safe. I can talk about how this works in reality in a second. So everything's fine. Now, this is not the entire picture, right? This is really not the entire picture. So even so we have this technical system like it is, in reality there is somebody sitting inside the cars. So for the time being, it's just a user. It's not the human is not yet interfering. It's just there. But even so, the human is just there. It may be that some people have constraints like, oh, well, I'm a bit afraid, why the safety gap is so narrow, I'm not feeling safe, please extend the safety gap. And on purpose, the guy with this shirt there in the back, more aggressive, it's too slow, come on, let's go. So there are already contradictory demands from the user, and it's only the user so far. And this is also not what really happens on the street. We have no 100% autonomously driving cars. We have essentially 100% human-driven cars. So it's not like, I heard in some speeches, yes, let's assume we have a couple of legacy cars that are human-driven and the others are autonomous. No, it's not like this. No, it's 100% human-driven and maybe a tiny percentage that's autonomous. And the autonomous cars have somehow to deal with that. And eventually, we have more users. And now I'm switching from the term users to humans on purpose. It's not just user. It's part of the system. Now we have maybe this elderly lady with this really cool old-timer here. Where definitely no computer fits, so that's also out there. No sensors, no nothing, no control. We have somebody who is about to cross the street, just another user, or human, sorry, who interferes with the system. We have experience or expertise from the others. This guy here passed this tree already, who saw this guy. So maybe you can just say, push a button and say, by the way, there is something unsafe, please, computers, be careful. So having the human as a helper here, and eventually, we cannot ignore this guy here. Eventually, we also have to deal with at least the possibility that somebody wants to maliciously attack the system. And if we ignore this possibility, then we will run into huge problems in the sector. Yes, please.
Yeah, just a comment. Really nice talk. You said if you can. So I saw some discussions that in the future, in the 20, 40 years, it will be completely forbidden to drive cars on the autonomous. So you are showing a different situation. Of course, there is like transaction to reach it, but what is your vision about that?
I'm very sure that we will eventually, I will not name any number, like 20, 30 years or so. Eventually, which is a nice word, eventually we will get there, that we have 99.99% fully autonomously driven cars. Yeah, exactly. But even so, we will eventually get there. What do we do in the meantime? How do we bootstrap the system? What do we do with the autonomous cars while there are still other cars around? And at the beginning, again, at the moment, it's 100%, 99.999 human-driven cars, and there's a small percentage of autonomous cars. Eventually, it will flip around, exactly. You're right. But how do we do this transition? Nobody knows. And this is a very interesting question. And this is, I'm using this this automotive application here, this use case here as an example. We have so many other CPS where the human is deeply involved in the system, and you have to deal with the situation. And maybe we can come up with some more fundamental solutions to the problem that we can also transfer to different application fields, where the same problem arises, that we have a CPS that is optimized for whatever the CPS is supposed to do, but the human user, both with expertise as well as some let's say deficiencies, so I'm not as fast as a computer, yes I am, that can still be handled, right? So that is, but you're right, at some point in time we might forget about this problem here, except that this guy will still be there and this guy will still be there as well. So, but for the rest, yes. So this elderly lady will go away because we forbid her to drive, maybe at some point. Let's skip this slide. This is not so helpful. So what I'd like doing is I'd like to promote a bit the idea to investigate a new type of a system. And this new type of a system is no longer just a technical system where we control everything. We write the software, we design the hardware, we derive control theory solutions, but there is something more than that. And this something more is the human. For this slide, I called it even slightly differently. That is called here cyber-physical-social systems instead of hybridized. It was a term I used before I started using hybridized. Again, to show that there's something more than that. And the very interesting thing is, and that is, to me, that is something I learned very late in my life, unfortunately, very unfortunately, but something that made my life much richer. This is no longer just a technical challenge, it's a socio-technical challenge, and that requires collaborations with interdisciplinary partners, and partners who speak different languages, actually. So talking to people from social sciences, psychologists, and others, it requires a warm-up phase, let's say it that way. And so I very fortunately had the chance to do that over the last years. From today's perspective, I think too late, much too late in my life, my research life. But now I have these interactions, and these interactions help me a lot to understand how to design technical systems in a better way. And also it's a lot of fun to do some interdisciplinary work, publish interdisciplinary, because it's so different than what you did before. So possibly, that is also some discussion I always have. Now, possibly when you are at a stage in your academic career where you this just is not in the bad meaning, right? Just doing your PhD, you will be evaluated how well you do in the disciplinary sense. So how well you do publishing papers in your field, to excel in your field, to show off in your field, to have a top publication on your main conferences or journals. So interdisciplinary work is sometimes a little bit of a burden to young PhD students. But the longer you are in the academic career, even at the end of the PhD, it's already something that enriches your life, your research life, where you can gain something from this. That is something I really like and I really enjoy. So let's go to some more into depth. So what does it really mean? And I took an example just to give you some idea of what we really have to do in terms of engineering in the field of automotive applications, CPS. And one of the applications that we are doing, of course, is platooning. So platooning, very simple, from the basic theory, a very simple application. You have cars driving with a safety gap autonomously, full stop. Can't be so complicated, right? Why is that complicated? Can't be. So the benefits are obvious, right? For trucks, it's mainly reduction in cost because of air drag is reduced, so you drive more efficiently. For non-trucks, it's not so much on the efficiency on that side. It's more on the efficiency in terms of capacity of the road. So the shorter the safety gap, the more capacity you have on the road. No? So more cars fit at higher speeds. So it sounds good. So it can't be so complicated. So what is platooning? Let's reconsider. When you're driving, all of you have driven a car, I guess. When you're driving, then typically, that's something you learned in driving school, typically you maintain a certain safety gap. The safety gap is depending on your speed and the so-called headway time. So this is the time that you need to pass a certain distance. So headway time is typically 2 seconds when you drive a car, when I drive a car. Most people think they are doing better and use less headway time, but it's a different story. Why do you need 2 seconds? Because there are 3 components in there. First, you need to perceive what's going on. That needs some time. Somebody's braking lights are flashing up. Somebody is seemingly to start slowing down. What shall I do in this time? Yes, I'm supposed to brake myself. Reaction time. And then finally, there's a physical part in the system, and that is the part where there's really a delay also from the time you press the brake pedal until you really decelerate. So something that is small but non-negligible. So these are the components, and that's why it's 2 seconds, which means about 50 meters at 100 kilometers per hour. 50 meters is a lot. Nobody maintains that. If you watch carefully, nobody maintains that. Let's do that autonomously. So many of you, I'm very sure, either own or have at least driven a car with an ACC, adaptive cruise control. Now, ACC is using typically radar, sometimes also camera-based techniques to measure the distance to the car in front, and then automatically brakes. So there's the measurement time here, radar time, and the brake time, of course, as well. So why is that a lot? You have to measure multiple times. No? So just once measuring distance does not give you any deceleration rate of the other cars. So you have to measure multiple times to get the duration of the second derivation, which is the acceleration, negative acceleration of the other car. So that is what you're doing. But you can do it even smarter. You can do yet another type of delivering this information to the following cars, and it's wireless communications. No? Then you have a communications link here, and then you have communication time in there instead of measurement time. Oh, sounds good. Sounds good. So possibly you can reduce these times. You see that on the slide, right? From 2 seconds to 1 second to 0.6 seconds. This 0.6 seconds still is 16 meters at 100 kilometers per hour. It's a lot, but you can't do much about this. You can't do much about this. And that is for one very reason, and that is, it's maybe not just 2 cars out there, it's maybe 3, 4, 5, 6. And if it's many of them, and you have 1 car decelerating, there's a side effect on the next car that has to decelerate even more because there's communication time in between. And the next car that has to decelerate even more because there's a communication link between. You know that from driving on the freeway, right? You see these shockwave effects. You see that from human-driven cars, as well as you can see that from these automated cars. But you can do something smart. You can do something smart, again, by means of communications, that you not have just links between 2 cars, but you link all the cars together. And linking all the cars together allows you to get rid of these oscillations using a smart control system. Smart control system, by the way, is the only formula I have in my slides, I promise. Smart control system essentially means that you need not just the information of the car in front of you, but also the information from the lead of the platoon, so that you know what the entire platoon is doing. So essentially what you control in your own car is your own acceleration. So you want to know whether you have to slow down or speed up. And by means of looking at the acceleration of the car in front of you, the acceleration of the lead of the platoon, the speed of the car in front of you, the speed of the lead of the platoon, and the distance to the car in front of you. Put that all together in a control theory system, and then magically everything works. No human in there. So we are currently, actually I could have added that to the slide, but we just submitted a very cool paper together with some colleagues in Australia, research network worldwide. In this paper, we looked into the possibility that one of these cars is not fully automated, but semi-automated. And semi-automated means that we have to accept certain reaction times from the user in there. And when we add these reaction times, then this leads to, we can design a new control system, that's a stochastic control system, that allows to have some additional reaction times from different users in there. It's an interesting problem, by the way. Extending, of course, all the safety gaps and so on and so forth. But we did it for one user, for one human-driven cars. Now consider we have multiple of them. So that's something we did not solve yet. So we can now do a lot of experiments. Experiments for us is typically, so from a methodology perspective, it's typically simulation. So because we are a small group here at TU Berlin, so we don't have 100 cars. Even if we had 100 cars, we don't have 100 licensed drivers to do safety critical operations without running in the end to liability issues. So, and also then, if we had them, we could do one experiment a day. With our simulation, we can do 10,000 simulation experiments a day, and we don't need licensed drivers, and there's no liability issue. So we did some experiments, just to give you an idea. And this is a super complex figure. I guide you through this. It's the only very complex figure, I promise. But it's something very interesting. What this figure shows you, looking from a telecommunication network's perspective, what this figure shows you is on the x-axis how frequently in time I send messages between the cars. You see beacon frequency, so it's going up from 1 hertz to 20 hertz, so 20 times a second I send a message between these cars. This is the control input that you get for the controller. Y-axis shows minimum distance between any car in any simulation of our system. I'm talking about minimum, right? It's not average, something like this. I'm interested in minimum because I want to see whether at any point in time cars get so close they crash into each other. If the distance is 0, I assume a crash already, right? I don't care whether it's critical or not. It's 0 is crash, full stop. So I never want to reach the line at 0. And what you see in the different colors here is different deceleration rates. So deceleration rates from 2 to 8 meters per second per second. By the way, 8 meters per second deceleration rate is something like a full stop. So if you hardly push the brake pedal, that is something what you get. So what you see is, let's just look at only one of these curves, the blue one. The blue one touches already 0 at a beacon frequency of 3 hertz. So obviously, communication needs to be enabled and somehow capable for sending more than 3 messages to the entire platoon per second. And not just sending, but particularly receiving. So successfully sending, reliably sending these messages. 3 messages. Let's say 4, to be on the safe side. Let's say 4. If we send 4 of these messages, we are safe. I have an animation that even says 5, but 4 would be good enough. So are we able to do that in our modern communication protocols? I already can tell you no. Whatever we're using. We did a lot of experiments. I have some graphs on that in the slides. I intend to skip these graphs because it's boring. What I can tell you is that whatever technology we are using, we are not able to do that at the moment. Why? If we are using a communication technology that is inherently based on CSMA, so carrier sense-based communication technologies, at some point in time, the amount of communications on the wireless channel is so high that already now, because of the increased load on the wireless channel, it takes more time for channel access. Number one, so it just takes more time for channel access. And secondly, channel access may go wrong, so 2 cars falsely think the channel is free, send at the same time, and we end up with interference, what we typically call collisions. That already means 1 message is gone. 1 message is gone means we are dead already. We can send, of course, at 10 hertz. If we send at 10 hertz, we can tolerate every second message being lost. But no 2 messages, consecutive messages in a row. So be careful about this. If we do not do CSMA-based techniques, if we do something that is like a TDMA schedule or resources allocated dedicatedly to us in a 5G network, it would work. So why did I tell it wouldn't? Because it would work for a very limited number of cars who get these dedicated resources, and then we are running out of resources. So we can allow 100 cars on the freeway. Then we have to block, because now we have no dedicated resources anymore. We have to wait until they are far away, and we can allocate the resources again to other cars. So the advantage of platooning, namely having tons of cars with safety gaps, very narrow, increasing capacity, gone. No? So we need to think a little bit about out of the box. Do we really need to send, let's say, 4 messages per second? Send and receive, right? Send and receive 4 messages per second. So if nothing changes, the only information I get is nothing has changed. So essentially, from an information theoretic perspective, is 0 information. Nothing changes. So why should I get an information that nothing changes? And waste my channel resources, my wireless communication channel resources. It's totally useless, right? So what we could do instead is first thinking about whether we need to transmit something, yes, no. If there is a strong need for this, then yes, let's do. How can we express this need? From a communication perspective, not at all. We need to get another input here. No, but fortunately, this is a fully automated system. Human is still not there. Fully automated system, so the system can tell us. And the system can tell us it's not the communication system, but the control system can tell us. The control system can tell us, at the moment, sorry, there's no need at all to do something. And we did some experiment on that. We designed a protocol that is called jerk beaconing. Jerk is a physical metric for defining what is the change of acceleration over time. So if we look at the change of acceleration over time, carefully acceleration, not speed or something like this, change of acceleration over time, that is the point when we cannot predict the system anymore. If just acceleration is positive or negative, we can easily predict the speed at a certain point in time. But if acceleration changes, we cannot predict anymore. So what we did is we looked at the change of acceleration, and then based on this change of acceleration, we designed a system that identifies, yes, there is need now to communicate, there is no need for communications. And this way, we are able to use the same communication resources, enable all the cars on the entire platoon, on the entire freeway to communicate, just using a different, let's say, a different sort process, looking at the problem, not just talking to telecommunication networks people, but talking to control theory people. So that's a good starting point. So that is enabling autonomous driving. So far, so good. Autonomous driving. Let's go back to the discussion that also we had just a second ago. Are all these cars autonomously driven? Yes, no.
Question?
Yes, please.
So did you look at it from an entropy point of view? Did you have the